Thank you. I am Tongfei Chen. I'm a PhD student at Johns Hopkins University. I'm working on artificial intelligence, natural language processing. I'm not a member of the PL community, so correct me if I say something wrong. Okay. In this paper, I talked about tensors. Tensors, what are tensors? Without all these mathematical jargons about tensor algebra or whatever, in computer science, it's basically a multidimensional array. Scalar variable like a float or a double would be a zero-dimensional tensor. A vector, a mathematical vector, is a one-dimensional tensor. A matrix is a two-dimensional tensor. And we could just generalize it to higher dimensions, like a 3 tensor. It's like a cube. Tensors are a core data structure in machine learning and the recent artificial intelligence boom. Like in computer vision, like image can be represented as tensors. In natural language processing, a word or a sentence or whatever could be are encoded in the system as tensors. These are especially useful in deep learning because tensors are differentiable. You can differentiate an algebraic expression with respect to a tensor. And because of their automatic differentiation techniques, we can enable machine learning by first-order optimization algorithms. We don't need to manually code up the gradient of an expression. We can just do it automatically. We're going to talk about that later. So first, we could see how we can encode stuffs into tensors. For example, this image. This is the famous baboon image used in computer vision. You see it has height and width. We first decompose it into different color channels like this, like red, green, and blue channels. And we just fold them together like this. So we get a cube. Is it clear there? Okay. So we get them folded into a cube where we have 3 dimensions, width, height, and channel. So this is basically a 3-dimensional array. Or in natural language processing, we have a function Thank you. We have a function called embedding that maps the set of vocabularies, maps each word to a d-dimensional real vector, and that is the embedding function. So for example, the phrase here, the cat sat on the mat, every word is encoded as a vector, so the whole phrase is encoded as a matrix. So a sentence or a phrase in natural language processing would be represented as a 2-dimensional tensor. So recently, there's this AI boom. There's lots and lots of machine learning tensor libraries. NumPy, Tiano by University of Montreal, TensorFlow by Google, PyTorch by Facebook, DINET by Carnegie Mellon, MXNet by Amazon, and Chainer by some Japanese university, I forgot. So what's the problem with all of these? These are all in Python, which is we just don't really like. We just don't really like. So we really want to have a Scala stuff. The reason that why we don't like Python but we like Scala is because Python lack expressive types. Image or sentences in these Python libraries are all belongs to just one type called tensor. This is not really fun to us, and we do not even know each axis is. So this is a line of code using Google's TensorFlow. We use reduce max. A is a tensor, reduce max, axis equals 1. This means we have a 3-dimensional tensor. We want to do a reduction over the first axis. But what is axis 1? We just don't know. You have to remember that clearly. We cannot use types to guide the programmers to code. So this makes the code very hard to debug and maintain or reason. I've been working in, this is my personal experience working in natural language processing. I always forgot what axis is in each tensor. And there's no type checking and compile time. We have lots of failure at runtime. Every time you just fail and then just get back to the Python code and tweak it a little bit. I'm not really sure if it'll work next time. It's a sense of insecurity which swells in your mind. It's not going to be safe. So we would like to have an expressive type system and type safety for tensors. Can we make them type safe and typeful? we would like to encode the meanings of axes. So a tensor, a 2-dimensional or 3-dimensional tensor, each axis has a specific meaning. We would like to encode them into the type. So a natural tool would be H-lists. That's the heterogeneous list. So we could have a tensor that's a trait or a type, whatever it is, or a class. It has a type parameter A, which encodes the axis, which is the H-list. So goal is just to create a typeful and type-safe deep learning tool in Scala. So during the next few slides, I would just show how we could do this in a very typeful way. For example, let's revisit again the image and the sentence. An image in Python will be just accessed in this way. It's just an array of a cube, then the first dimension is width, second is height, the third one is channel. You have to remember them by heart. But in Scala, we probably could do this. An image would be a tensor of width, height, channel, and h-nil. So at compile time, we have every information we need. So this would be encoded as tensor width, height, channel, nil. This would be word embedding nil. So first, the programmers are relieved to remember all these axes in their mind. So the next topic we're going to discuss is type safety. Tensors, you can add, you can multiply, you can do convolution on them, you can do a lot of these basic operations on them. Operations on tensors are only allowed if their operand's axis makes sense mathematically. For example, we have a vector. This dollar sign is h-nil. This is a shorter notation. So if we have a tensor of A plus another tensor of A, okay, this is vector addition, okay. But we have a tensor of A plus a matrix, doesn't compile. A tensor of A plus a tensor of B doesn't compile. These are both vectors, but they mean different things. We want to achieve this. Or if we had a matrix multiplication, Z equals X times Y, if we have a matrix multiplication of a vector and a vector, doesn't compile, they are not matrices. If we have a matrix of the same shape, it doesn't compile, because for a matrix to multiply, you have to have the AB times BC. You get a matrix of AC. That's matrix multiplication. We would design ways in Scala to make all these, make the first two cases do not compile, and the third one just compiles normally. So start from here, we would introduce some of the basic constructs in deep learning algorithms, deep learning frameworks. The most important thing is the computation graph. So here, this is like a classifier. In a machine learning, this is a classifier. X is the input, Y is the gold output, L is the loss function. So Y hat is your model's predicted outcome. So Y is the real outcome. So by comparing Y hat and Y, we got a loss function, so we could train upon it. So these are parameters to the model, and H are the intermediate results. So this is the input, these are parameters, these are intermediate expressions. This thing in a lot of Python and C++ libraries is called a computation graph. In Scala, we could just easily encode them as a CO trait of expression X, which is an expression of something. The type is there. The type is X in generic. In Python, they don't have type. It's just called expression. So we have input, which is just a placeholder, has nothing in there. A parameter has a mutable value in there, which is the mutable value of that parameter, which in each iteration of the training gets changed. So we use a mutable state in there. It has to do that. And there's a constant, and this is apply. Apply is like lambda application, where you have an operation here, and you have an operation here, and you have an expression. If you apply an operation of x to y, upon an expression of x, you got an expression of y. So we here support unary, binary, and ternary operations. So this is basically a generalized algebraic data type in Scala. For my own experience, there's some, like, when you're pattern matching over these, there's slightly different problems in Scala. It's like pertaining to existential types, but that's not really a big issue. To let the whole neural network differentiable, that's for training, we need the whole network to be differentiable. The operators must be differentiable. So to be differentiable means it supports backward computation. So basically, the gradient of, so y equals fx, and the gradient of the loss with respect to x is the, by chain rule, is the gradient of the loss with respect to y times the partial derivative of y given x. We encode this as a trait called this, like operation 1, x to y, has a name. This name is for debugging purposes. And you can apply it to an expression of x to an expression of y by just wrapping it around in the case class to create a new node in the computation graph. And the forward and backward is the actual implementation of the math underneath. So forward is given an x, produce a y, backward given a, this dy is this term, y and x given an x. We can just extend it to binary operators, where it's op2. Op2 has like 2 backward functions that computes the gradient with respect to the first operand and the gradient with respect to the second operand. But these still have a problem here because, so here, our operations here are x1 and x2. They're refined to just one type. But we have said earlier we want it to be applied to, for example, addition, add. We want it to be on just vector of A, vector of B, vector of C, or a matrix of AB, matrix of AC, or cube. We want them to be type polymorphic. To enable type polymorphism, we encode such a thing called polyop. It's like polymorphic operator that has a F in there. F is an instance. F is a higher kind of type that is a subtype of op. Op is the grounded operation, and polyop is the type polymorphic thing. We have this. So to apply it on any x or any expression of x, we require an actual operator be found here. The f is implicit here. So the operation polyop1, f, can only be applied to an expression of x if an implicit instance of fxy is found. So if found, then the resultant type is expression of y. If not found, it doesn't compile. So an object of fxy is basically a proof that witnesses the fact that an operation can turn x into y. Just like proof, we do this validation at compile time. This is very similar to the polymorphic function in shapeless. So this is like similar to the shapeless poly1, and this f is similar to the shapeless case.ox. The case.ox here, we need them to be differentiable, so it's like slightly different from case.ox. So let's encode some operations in tensor algebra into this framework. We start with the easiest one, is negation. So we have a tensor, we're going to negate it. So we introduce a neg-f. Neg-f is the f. Neg-f xy. If we had an implicit instance of it, it's proof that x, if we negate x, it turns into y. So we have a annotation here, implicit not found, cannot apply negation to x. So this produces a very user-friendly compile message. If we just did something wrong, the compiler would just say, located at a specific site of the operation application, that's it. This type doesn't work here. So neg-f has 2 implicit instances. First is a scalar, and first a tensor. Basically, it encodes such propositions. Is for any type R, if R is real, indicated by the type class instance here, then we know that if we negate f, we negate R, it turns into a R. Or here, in the tensor case, so if we have a tensor T, R, and A, so if T is actually a typed real tensor, it's a type class, then negation of TA turns into TA. So these are 2 cases that this could be done. So this is so we ensure that this negation operator can only be applied to expressions of these types. Because of the recent Dotty design, I would like to write this in this way. This is my proposed Dotty syntax. I don't know if this is currently possible in Dotty. So this neg-f would be an enum, and the 2 cases would be implicit case. I don't know if Dotty supports implicit case now, but this is really what I want for this. So this is negation. The second example is matrix multiplication. Basically, we encode this proposition. It's for any type ABC, if T is a typed real tensor of R, so here T might be a tensor implementation on a CPU or GPU, R would be just float or double. We know that when you multiply T of AB and T of BC, we get T of AC. So this is encoded. Okay. This is encoded in the type system here. Another example, more complicated, is sum reduction. For example, we have a tensor, three-dimensional tensor here, A, I, J, K. We want to reduce along axis J, just eliminate this axis. So we got a resulting tensor of B, I, K. So how do we do this? We encode this thing, this proposition into the type system. It's like if T is a tensor of R and the H list A, if we remove a type U in it, returns in a B, we know that if we sum along TA along the axis of U, we got TB. So here, to encode this proposition, we use shapeless here, remove.aux. So this is a shapeless operator that we could do this. So we have a very safe sum reduction algorithm here. A more complicated example would be contraction. This is a generalized form of a lot of linear algebra operators like inner product, matrix multiplication, tensor product, or whatever. It's basically we have two tensors of arbitrary dimensions. We want to align some of these here, J here, and these aligned axes are summed over. So they're gone in the output tensor. So this is variously called einsum or tensor dot in various Python libraries. This is quite crucial in a lot of deep learning applications. So we proposed natural contraction, which is because in Python you would say that if give A and B, we want to contract the first axis of A and the second axis of B. That's how we write in Python. But here, because we have type tags on each dimensions, we would like to just like inner join in databases, we just join those axes with the same names. So given tensor of A and tensor of B, we output tensor of C, where C is the symmetric difference of A and B because the aligned axes are summed out, they are gone. So this is widely used in machine learning. I don't have time to elaborate on this algorithm. Okay. So basically we encode this trait here is just if the symmetric difference of A and B is C, A, B, C are both H lists, we know that if we contract TA and TB, we got TC. So here we need to write the simdiff.aux ourselves. This is not there in shapeless. So in here, this operation has a very elegant property here. Is, for example, you wonder if it type checks, but it actually do because the symmetric difference of A and B and then symmetric difference with B recovers A. So this type checks. This is a very pretty elegant property. So now let's look at some of the more complicated thing in machine learning. For example, this is recurrent neural network. This is just like, for example, we have a sentence. I have a lot of words in here. We want to fold them over the words to get a final state that encapsulates the information we have learned throughout the sentence. So this is basically a fold or scan or etc. So we can reuse the Scala, the native Scala operations on collections. So if we want all of these, we use scan. If we want the last one, we just use fold. And that's just very natural in Scala. Or we could have recursive neural network. For example, this also very popular in natural language processing. For example, we have this phrase, the cat sat on the mat. This is the syntactic analysis of this phrase. MP is a noun phrase, PP is a preposition phrase, VP is just a verb phrase, and this S is a sentence. So we just fold along this tree up to the state. So we got some information over the whole sequence. So this is just a generic fold or catamorphisms in PL jargon. So we could express these in Scala just very easily. I have implemented some of the example networks, for example, like this. This is just the image classification network implemented under this framework in Scala. So we just create a label in. In is just a label, it's just a phantom type. We have one instance of it, it's just a label. So X is the input of tensor in, Y is a vector of tensor out. We have three neural layers that maps into hidden, hidden to hidden, hidden 1 to hidden 2, hidden 2 to out, and these are a number of dimensions. So we have a Y hat is X, pass through L1, pass through a neural activation function, pass through L2, pass through activation function, pass through L3, and pass through softmax. This is normal machine learning. And we got a loss function, which is the cross entropy, the loss function of Y as the goal output and Y hat as the predicted output. So then we can do backward computation. We can do automatic differentiation over this computation graph. So this is very concise and expressive. I would say much more than a lot of Python libraries. So, so future work for this, I would like to further complete this towards a fully fledged Scala deep learning engine. We could have automatic bashing, which is fusion of different computation graphs, to put a lot of graphs together into one graph to run it concurrently on a GPU that makes it much faster. GPU support with CUDA using Swig. Multiple backends. There are already multiple Python libraries already written there. Their core is C++. We can just reuse this course. We don't want to do C++ ourselves. And type-safe higher order gradients or distributed learning, doing deep learning over a cluster using Spark. We can just pass the gradients around using Spark. So the goal is just we could have a type-safe and typeful, declarative, succinct, and very, very expressive deep learning system in Scala. Thank you.
Hi, thanks for your talk. So I had a question about recurrence in neural networks, right? Maybe I missed it, but...
This one? The tree one or a sequence one?
Right, so how do you encode, so I'm not sure if the term is right, but don't you have like these special neural networks in which some of the output signals are fed back into the input?
Yeah, this is what it is.
Okay.
So, this is recursive, right? Like the S, some people write, they draw graphs, the S is just one node, they just keep feeding X into it. I'm just unrolling that graph to as a sequence.
Okay, I see.
You can consider this as somewhat similar to a automaton, where S is the state and X is the input to the state.
Okay, I see. So, but the nodes represent computations, right, in this graph, right?
Yes.
But you have a finite number of them here.
What?
You have a finite number of them here.
Yeah, X is the length of the input. So this is a sentence, like the cat sat on the mat. So each X is a word in natural language processing.
Okay. This doesn't have to do with any, I mean, I know a little bit about neural networks and this stuff, but I thought that there was some neural networks in which you actually feed the output signal back into the input. Is this the case here?
No.
No.
No, usually in neural networks, the computation graph should not have cycles.
So
it should at most be a DAG, a directed acyclic graph.
Okay, I see. So, but can you represent this kind of stuff, or how would you do it if you had to?
You have cycles in it?
Right.
If you have cycles in it, you cannot really do automatic differentiation, because when you do automatic differentiation of the graph, it is basically a reverse computation on the graph, or in PL jargon, it's just like another interpretation of the free monad, basically. So I don't know if you could have cycles in it, how would you compute it? Usually we don't have cycles.
Right, okay. Well, I mean, you could take the last output and kind of feed it back, or have some memory or...
Oh yeah, you can feed this to another stuff. You can stack another layer on top of it and use these S1 to Sn as the input to another layer. You can do that.
Okay. Okay. Maybe we can talk offline, I guess.
Okay. Thank you. Thank you.